Why does a simple fork in a microwave suddenly spark like a tiny lightning bolt? At first glance, it feels like magic, or worse, like dangerous radiation. But the truth is far more interesting. What you are really seeing is physics playing out in your kitchen, turning an everyday appliance into a stage for one of nature's most dramatic effects: concentrated energy at sharp edges. To understand it, we need to step inside the world of invisible waves and metals that dance with them. A microwave oven is not just a metal box with a light bulb. It's more like a concert hall where one instrument plays only one note over and over. That note is a specific frequency of electromagnetic waves, tuned to make water molecules vibrate and heat up. These waves bounce around inside the chamber, creating standing patterns of energy, like ripples in a bathtub when you shake the water at just the right rhythm. Normally, food absorbs those waves and turns them into heat. But when you put metal inside, things get interesting. Metal behaves very differently from food. Food lets microwaves penetrate and wiggle its molecules. Metal pushes the waves back, like a mirror reflecting light. But unlike a perfect mirror, metal has surfaces, edges, and corners. Imagine water flowing smoothly around a boulder in a river. Most of it glides past, but if the rock has a sharp point, the current whirls and gathers there. In the world of microwaves, the same thing happens. Energy crowds into sharp edges, piling up instead of spreading out. And when energy piles up, sparks fly. This is why a fork or crumpled piece of foil can suddenly turn into a miniature lightning generator. At the sharp tines of a fork, electric fields grow so strong that they can rip electrons right out of the air molecules nearby. Air, usually an insulator, suddenly becomes a conductor. Electrons race across the gap, collide with other atoms, and trigger a chain reaction. That's the spark you see. A plasma, the fourth state of matter, right inside your microwave. It looks dangerous, and it can be, but it's also a clear window into how electromagnetic energy concentrates itself at points and edges. To make this clearer, let's use a simple analogy. Picture a crowd at a concert. If people are evenly spread out across a big stadium, no single spot feels too crowded. But if everyone rushes to the front row against the barrier, the pressure there skyrockets. Sharp edges in metal are like that barrier. They focus the crowding of energy into one tiny place. And just as too much pressure makes people push and break through, too much energy density at a metal point makes electrons break free and spark. You might wonder, if sparks are possible, why doesn't every spoon or metal tray burst into fireworks? The answer lies in geometry. A smooth, rounded spoon reflects microwaves without giving them a sharp point to crowd into. The waves spread out evenly and nothing extreme happens. A fork, however, has multiple tines, each ending in a needle-like tip. That's like placing tiny lightning rods inside the microwave. Each tine becomes a place where energy concentrates. Add two tines close together, and you get a gap where the field can leap across, creating arcs that look like little bolts of lightning. Think of it like a thunderstorm in miniature. In the sky, clouds build up electrical charges. When the charge difference between cloud and ground becomes strong enough, the air breaks down and a lightning bolt strikes. In the microwave, the waves feed energy into the fork until the air around the tips can't hold back anymore. Then, pop, a spark jumps, like a scaled-down thunderstorm happening between metal points. But there's another layer to the story. Remember, microwaves are not just any random energy. They're oscillating electromagnetic fields, flipping back and forth billions of times per second. That rapid oscillation means the spark is not just a one-off discharge. It can be driven again and again by the alternating fields, creating flickering arcs and even sustained plasma if conditions are right. What looks like a single spark is actually the metal and microwaves performing a high-speed dance. This is why crumpled aluminum foil is notorious in microwaves. Each wrinkle creates tiny sharp edges like mountain peaks. Each peak is a candidate for concentrated fields and sparking. Smooth foil pressed flat against a dish often causes no problem. But introduce crinkles, and suddenly the foil becomes a landscape full of lightning rods. That's why microwave instructions always warn against crumpled foil, but sometimes allow carefully smoothed foil coverings. It's not the metal itself that's the villain, but the geometry that turns it into a spark factory. Now, let's add another analogy, one that really brings this home. Imagine kids playing with magnifying glasses in the sun. A smooth glass spreads light across a large area, just like a smooth spoon spreads energy. Nothing unusual happens, but tilt the glass just right, and sunlight focuses into one tiny burning point. Suddenly, paper bursts into flame. Sharp edges on metal inside a microwave are like that magnifying glass. They don't create new energy, but they focus the existing energy into such a tight spot that it becomes powerful enough to change the state of matter. This also explains why not all sparks are equal. A thin piece of foil might just flutter and glow for a moment. A fork tine, closer together with another tine, might generate repeated arcs because the microwaves keep pumping energy into that confined gap. In extreme cases, people have even seen persistent glowing balls of plasma form inside microwaves, like tiny artificial lightning storms. These are rare, but when they happen, they're a breathtaking demonstration of how concentrated energy behaves. Of course, all of this might sound like the microwave is unsafe or radioactive, but here's where the aha moment comes in. Microwave ovens are not dangerous because of radiation in the sci-fi sense. They don't make food radioactive, and they don't produce nuclear reactions. The sparks you see are not proof of something sinister. They're simply electromagnetic fields concentrating at sharp edges, the same principle that makes lightning rods protect houses by giving energy a place to discharge safely. Your kitchen isn't becoming a nuclear lab. It's just physics revealing itself in a very dramatic way. So the next time you hear someone say, "Never put metal in the microwave, it's dangerous," you'll know the full story. It's not the metal itself that's the issue. It's the shapes and edges that matter. Smooth metal reflects waves harmlessly, while sharp points and wrinkles act like lightning rods, concentrating energy into sparks. And those sparks are simply electrons breaking free, just as they do in a thunderstorm. But there's one more fascinating detail we need to explore before the picture is complete. Remember, the microwave chamber itself is made of metal. So why doesn't the oven constantly spark just from its own walls? The answer lies in design. The chamber is made of smooth, rounded metal surfaces, carefully engineered to contain and reflect microwaves without sharp points. Even the little mesh you see on the door is designed with precision. The holes are small enough to keep microwaves in, but large enough to let visible light out. Your oven is already a metal box. It's just shaped in a way that avoids creating sparks. This shows us something profound. Sparks aren't random acts of danger. They're a predictable outcome of how waves and materials interact. And once you understand that, a microwave stops being a mysterious black box and starts looking like a controlled physics experiment hiding in plain sight. It's the same laws of electromagnetism that govern antennas, radios, lightning storms, and even advanced particle accelerators, all condensed into the humble act of reheating leftovers. And this is the real magic. The kitchen spark isn't magic at all. It's nature showing us that sharp geometry can turn invisible waves into visible fire. It's a little piece of thunderstorm physics, scaled down to fit inside a box on your counter. And when you see it with fresh eyes, you realize that the fork in the microwave is not a mistake. It's a demonstration of one of the most powerful principles in science. But here's the twist that makes it even cooler. The very same principle that causes sparks in your microwave is used deliberately in advanced technology. Engineers design antennas with sharp tips and carefully chosen shapes so that electromagnetic fields concentrate exactly where they want them. Lightning rods on buildings work for the same reason. They don't magically attract lightning. They simply offer a sharp point where electric fields concentrate, giving the bolt a predictable path to follow. What seems like a kitchen accident is actually the same physics that keeps skyscrapers safe during storms and makes your smartphone connect to the internet. Think about that for a second. A fork sparking in your oven, a lightning bolt splitting the sky, and a satellite antenna transmitting signals across the world are all connected by the same underlying rule: energy crowds at sharp edges. This is one of those eureka moments where you realize that nature doesn't change its mind depending on scale. The same law of electromagnetism applies in your kitchen, in a storm cloud, and in orbit above the Earth. Once you see it, you can't unsee it. Let's explore another layer. Many people think of microwaves as mysterious beams, but really, they are part of the same electromagnetic family as light, radio, and X-rays. The only difference is wavelength. So when you see a fork spark, you're watching the same fundamental interactions that govern light bulbs, lasers, and Wi-Fi routers. It's a reminder that the everyday world is saturated with invisible waves, and metal objects are constantly responding to them. The difference is that in most cases, the geometry prevents anything dramatic from happening. Only when the waves are confined, powerful, and focused at sharp points do they leap into visible sparks. You can even imagine your microwave as a kind of laboratory. Every time you heat leftovers, you are sending billions of oscillations per second bouncing around in a chamber designed to contain them. Usually it's just food vibrating gently and warming up. But the moment you introduce a crumpled foil ball or fork, you are introducing experimental equipment, points and gaps that reveal the hidden drama of electromagnetic fields. It's like having a particle accelerator scaled down to countertop size. Safe, contained, but still capable of giving you a glimpse into the raw mechanics of nature. Now let's zoom out and think about how this knowledge changes perspective. People often assume sparks in the microwave are signs of something breaking or failing. In reality, they're proof that the physics works exactly as expected. The energy is there, the waves are oscillating, and the geometry of the metal simply concentrates that energy into visible discharges. It's not malfunction. It's demonstration. The same demonstration you would see in a physics lab with Van de Graaff generators or Tesla coils, just happening on your dinner plate. And this brings us to a practical insight. If you understand that sparks are about geometry, not just metal equals danger, you can see why certain uses of metal in microwaves are actually safe. Microwave-safe foil covers with smooth edges folded neatly don't spark because there are no sharp points to concentrate fields. Microwave engineers even use metal racks inside ovens, but those racks are carefully shaped to avoid dangerous arcs. The rule is clear: smooth and rounded, no problem. Sharp and crumpled, mini lightning storm. Once you know the rule, the mystery disappears, and what looked like random chaos becomes predictable science. There's also a poetic side here. Every time a fork sparks, you're seeing electrons, the tiny building blocks of electricity, ripped free and accelerated. They smash into air molecules, creating a plasma, the same state of matter that fills the sun. Think about that. Your humble microwave, designed to heat soup, can also produce the same fourth state of matter that blazes at the core of stars. That's why scientists love using microwaves in experiments. They're not just appliances, they're compact, accessible windows into plasma physics. And here's the real wow moment. Plasma created in your microwave is not fundamentally different from the auroras that dance in the night sky, or the flashes of lightning that split the clouds. The same physics, scaled differently, plays out everywhere in the universe. In fact, most matter in the cosmos exists as plasma, not as solid, liquid, or gas. That spark in your kitchen isn't an accident. It's a glimpse of how the majority of the universe actually behaves. So the next time you're tempted to test what happens if you put a fork in the microwave, don't, because repeated sparks can damage the appliance. But do remember what's really happening. Waves of energy crowd into sharp tips, electrons break free, and you witness the same forces that shape storms, power the sun, and carry signals across the planet. Suddenly, your kitchen feels less ordinary and more like a portal into the fundamental fabric of reality. And that's the hidden beauty of science. Even the accidents and warnings on your microwave door are invitations to wonder. They tell you that the universe is not random, but structured by rules that repeat from the smallest sparks to the largest galaxies. A fork sparking in the microwave is not just an annoyance, it's a clue. A clue that you live in a world woven by electromagnetic fields, where sharp edges can turn invisible waves into visible fire. So next time you see that flash, don't just think danger, think demonstration. You're witnessing the same principles that guide lightning bolts, protect skyscrapers, and connect cell towers. It's physics unfolding right before your eyes, proof that the ordinary can become extraordinary when you know what to look for. And here's the takeaway. Curiosity is the real power switch. When you ask, why does metal spark in a microwave? You're not just solving a kitchen puzzle. You're unlocking a principle that stretches across nature and technology. And if you want more of these hidden keys to understanding the world, more stories that turn accidents into insights and appliances into classrooms, then stay curious, share this spark of wonder with a friend, and subscribe to How It Actually Works. Because every spark, every question, every strange little detail is a doorway to a deeper truth about the universe we live in.